Hi everyone, I'm Yanhui Ma, a quality engineer from the virtual networking course team. And today I'd like to share the Userspace network datapath solution for both containers and VMs, and also share the performance benchmarking compared to the kernel datapath solution. Here is the agenda, and I will start with a quick project background. Actually, the project is still in the proof of concept. So it is not officially part of the OpenShift, and it is a cross-team effort with different parts owned by different team. And actually, the project is built on the hardware vDPA and is an evolution of it. Here are our some core members in the project. And the ultimate goal of the project is to replace the OpenShift current kernel datapath with the Userspace datapath. As we know, the OVNK is the default CNI is the OpenShift, and its datapath relies on the OVS kernel module. With the VDUSE and OVS-DPDK, the datapath can be moved into the Userspace. But before we productize it, we need to fully evaluate its benefits and trade-offs. So what's the benefits of the Userspace datapath? The first one, it offers a unified datapath for both VMs and containers. In the OpenShift, running both containers and VMs, typically the container will use the OVS kernel datapath, while VM use the Kernel-Space vhost-net and the Userspace, or use the Userspace vhost the user solution. But VDUSE will unify these different datapath backends into a single Userspace solution. It will reduce the development and maintenance complexity. And the second one, it will provide a better resource isolation. With the kernel datapath, the network processing happens on all the CPU cores, and with the Userspace datapath, we can pin the network processing into the specific CPU cores to avoid the competing with application, which can improve the stability and provide and avoid the contention. The last one, it also can give a more predictable latency since we bypass the kernel network stack. It avoids lots of interruption and the contact switching. Before we introduce the videos, let's briefly introduce the hardware vDPA. The vDPA stands for the Virtual Datapath Acceleration. It leverages the hardware NIC to accelerate its datapath. Its two main components are the physical NIC and the vDPA kernel framework. In this setup, we can see the virtual datapath can be directly implemented in the physical NIC. But considering the virtual control path is hard to be implemented in the physical NIC, so the vDPA kernel framework is introduced to translate the vendor-specific control path into the standard virtual control path. And there are two ways to expose the vDPA device. The first one is through the vhost subsystem. It provides a character device for the Userspace processes, like the QEMU, and another is through the kernel network stack. and it will provide standard Linux network interface on the host for the container. So in this, the hardware VDPA has already unified the data path, but it relies on the hardware physical NIC. Since we have already the vDPA kernel framework, the vDPA device also can be implemented in the software, either in kernel space or in user space. What a user space implementation is what we call the VDUSE. It stands for the vDPA device in user space. It removes the hardware dependency and also still use the previous kernel vDPA framework. It can bring the three main advantages comparing the hardware vDPA and the kernel space implementation. The first is fast and flexible development. It is not limited by the strict kernel code review and the hardware limitation. The second is it doesn't require the cloud providers to purchase and deploy the specific vDPA NIC. And the third one is the low maintenance. Upgrading a user space application is much easier than upgrading hardware and the kernel module. This picture shows the basic idea of the VDUSE. First, it removes the physical NIC and its relevant drivers, and also introduce a new kernel driver called the VDUSE driver. It bridges the VDUSE device and to the kernel vDPA system. To implement and expose the VDUSE device, we need two components. One is the VDUSE daemon. It implements the device emulation and also implements the virtual datapaths for the packet request. And another one is the VDUSE module, just like I shared in the last slides. It's a new kernel vDPA driver. And how the VDUSE, vDPA, and OVS-DPDK are connected and integrated in OpenShift. Actually, in the use case of OpenShift, the VDUSE daemon is implemented via the OVS-DPDK. OVS calls into the VDUSE driver via our control to create the VDUSE device, and the VDUSE driver then expose a character device for the control path communication, and then we use netlink bound the VDUSE device with the vDPA bus, which can open up the kernel path from the container and the VM to the OVS-DPDK. The control path shown with the black lines actually use the character device, but for the data path shown with the red lines, it used the shared memory, no need to through the character device. This picture shows the data path changes in the OpenShift. The left figure shows the OVS kernel bridge with the veth pairs. Its data path type is system. And the right figure shows the OVS-DPDK bridge with the VDUSE device. Its data path type is netdev. I will skip this part for the time limitation and move on the benchmarking. To understand the VDUSE performance, we run some benchmarking tests and compared the results with the veth. Here are the specific hardware and software information we used, and also some performance tuning. For example, the isolated CPU cores in the same Yanhui Ma node to the OVS-DPDK PMD threads and vDUSE RQs, and also the benchmark tools run on the same Yanhui Ma node. The test scenario is 2 ports on the same host, and we cover both layer 4 TCP test and layer 2 PBS test. Here is the test scenario. Let's start from the first chart. It shows the TCP throughput performance. The blue bar is the vDUSE and the red bar is the veth. We test the packet size from 128 byte to 1 megabyte. As we can see, for the small and medium packet size, vDUSE is on par or even better than veth. But for the large packet size, vDUSE reaches a plateau, and while the veth is still scaling up as the packet size increases. So that's where we can see a gap for some packet size. And this picture shows the TCP latency, and the pattern looks quite similar with TCP throughput. For the small package, vDUSE has advantages, but for the large packets, vDUSE falls behind. And besides the mean latency, we also compared the standard deviation of latency. For the small and medium packet, vDUSE gives the smaller standard deviation. So these values can prove the more stable latency advantage we mentioned earlier. Then let's look at the TX PPS performance. For this test, we covered for 64 bytes to the 1 kilobyte across all the packet size. vDUSE can consistently achieve the higher TX PPS than veth. If we look at the RX PPS, it matches what we saw on the TX side. vDUSE is higher than veth. So in the performance, TCP doing well in the small or medium packet size, but for large packet size, there is still some gap, and this is an area we are still analyzing. And on the function side, the basic vDPA feature has been supported on the downstream kernel and OVS, but the more advanced function is still and development in upstream. And besides the container, we're also working on the support on VMs, such as the VM migration, vDUSE device. So in order for the vDUSE project, in both performance and function, we are working on more it. Yeah, I think that's it.